Okay, now let's actually go to the main part of this topic, and this is where most of the questions will be asked. So let's take an example of this equation. Sodium solid plus Cl2 gives you NaCl. But to balance the equation, we'll have to keep half over here. Now, as you can see, what type of enthalpy change is this? This is the enthalpy change of formation, right? Because you are forming the compounds from its elements under standard conditions. Now, sometimes what happens is that we have to find the lattice energy of an ionic compound. So, if you want to find the lattice energy of an ionic compound, it's very hard for us to measure the lattice energy directly. So what we do is we use a Hess cycle, right? So we use a Hess cycle to measure the lattice energy of a compound. Now, if we have an equation like this, can we make a Hess cycle out of it? We can. How can we do it is if we break this NaS plus Cl2 down into two roots. So instead of going directly from here to here, we can make an intermediate in the middle, and then from here we can go to NaCl. Let's visualize this. So here down we can keep an intermediate. So what we want is we want to find the lattice energy. That's our goal. Now, what is the definition of lattice energy if you remember? Lattice energy is the enthalpy change when 1 mole of an ionic compound is formed from its gaseous ions, right? You need the gaseous ions. So in NaCl, we have two ions, Na and Cl. So we have to make the gaseous form of this ion. So we have Na plus as a gas plus Cl minus as a gas as well. So this will be our intermediates down over here. And we will be looking to go from here plus this one. So let's say this one is delta H. Let's just call it delta H. This one will be delta H lattice, right? Why is this lattice energy? Because you're going from the gaseous ions to the ionic compounds. And this one, the main one, is the enthalpy change of formation because you are forming an ionic compound from its elements under standard conditions. Now, the tricky part is what is this delta H? And this is where a special type of Hess cycle called a Born-Haber cycle will come into play. And we will be using this to find out the lattice energy of an ionic compound. So before we actually do that, let's make a general equation out of this. So remember the vector law that if this is the tail and then this is the head and then this is the tail, this is the head. We can combine these two vectors to form the main one, right? So delta H plus delta H lattice will give you delta HF. Okay, so this will be our general equation. Delta H plus delta H lattice gives you delta H of formation. So most of the times we calculate this using values which were given, and most of the times this is given as well. So it can be either way. They might ask you to find formation, they might ask you to find lattice energy, but whatever the case, we will have two values and we'll have to find the third one. So one more thing to note down here is that you might see that sometimes this equation is not written like this. It might be written the other way around. So for example, they can keep this part in the reactants and they can keep this part down over here. But whatever the case, what you have to identify is that how the arrows are going. So the main concept here is that you have to try to play around with these three equations. The most likely there will be formation, there will be lattice energy, and there will be delta H. So however the way it's arranged, what you have to do is try to form an equation out of it and then try to solve it. So let's look at an example of the Born-Haber cycle of NaCl and how we can go about solving this. Okay, let's actually draw the Born-Haber cycle for NaCl. Now, your first step is to write the reactants of the reaction. So remember we had Na as a solid plus half Cl2, which was a gas, right? So this was our reactants of the equation. Now, from the reactants, look at what the change happened. The sodium solid turned into sodium gas, and also it lost an electron. That's why it became a positive ion. Also, Cl2 became a Cl atom, and also it gained an electron, right? So we can see from here that these four changes happening. The first one is the change in state here, Na solid to Na gas, the ionization energy or the loss of electron, and then Cl2 atomization, and also the electron affinity because it's gaining an electron. So all of these we have to represent it in our Born-Haber cycle over here. So what we do is that the first thing which happened here, we say that sodium solid became sodium gas. Right? So you write this again: sodium gas plus half Cl2. Yes, you just leave the Cl2 as how it is. You concentrate on only one thing at first. And this was the enthalpy change of atomization. Right? So this is our first change. Now, another important thing to note here is that a Born-Haber cycle is actually an energy level diagram. And in an energy level diagram, when you go up, it means that the reaction is endothermic. And when you go down, it means that you are losing energy or it's exothermic. So atomization, we know, is always endothermic, and that's why the arrow is going up, right? So that's our first step done. The second step is that we also have atomization of chlorine, right? So this Cl2 is also becoming Cl. Or you can also go for ionization energy of sodium. Either way, it doesn't make a big difference. At the end of the day, you'll get the same answer. So let's say you go with the sodium one first. So this will be Na plus gas plus half Cl2. Gas will remain as how it is. Right? This will be our second energy change, and this will be the enthalpy change of ionization energy, and it's the first ionization energy. Now, also one thing to note down is that why didn't we go straight from Na solid to Na plus? That's because for ionization energy, remember in the definition, the reactant has to be in gaseous state, or else it's not called ionization energy, right? So we have to convert this into gas first, and then we have to remove an electron from it. So we can't just go direct to Na plus. Okay? So that's our second step. Now our third step also will be, so we are done with the Na plus part. Let's go to the Cl. For the Cl, we see that we can also have atomization, so it's going to be plus. Sorry, one more thing that I forgot here is that we lost an electron from Na, right? So Na become Na plus. So we have to add the electron which we lost from this equation, right? So Na became Na plus plus electron. So this electron is what I've added over here. Hope that makes sense. Right, let's continue. So the next one, we say that the chlorine will become an atom. So this is going to become just a Cl gas, and our electron is still going to remain. Right, this will be our next energy change, and this will be delta H atomization. Now the last one here will be the electron affinity of chlorine. And remember, electron affinity, the first one is exothermic. So instead of this going up again, it's going to go down this time. So we will have something like this. This is going to go down, and you will remain with the same sodium ion. But because chlorine will now gain this electron, it's going to become Cl minus as a gas. Right, and this is delta H electron affinity. Right, now when we get this Na plus plus Cl minus, we have already accomplished what we wanted. We wanted to get this intermediate, and that's what we have achieved. Now the next direct thing will be to go from this to NaCl, and this is lattice energy, right? And lattice energy we know is exothermic. It's always exothermic. So again, our energy change will go down. Now, how down should we go? Should we go from here to here or from farther down from the reactants? Now, to know this, uh, look at what your overall equation is. This is an enthalpy change of formation, right? And we know that enthalpy change of formation is exothermic. So this is exothermic, which means that the overall energy change will be less So we will go down, we will go further down than the reactants. This will be much lower, so the products will have less energy than the reactants. That's the energy change for the overall equation. So which means that over here we have to go further down as well until this point. So that we could show that this reaction is exothermic. So the products for this will be NaCl as a solid, right? Just that. And this will be your delta H lattice. Then from this reactant to this products, this will be your delta H of formation of NaCl. Now we can make an overall equation out of this. You see, this is actually very similar to a Hess cycle. It's just that the way it's drawn is different. So this one, this part over here, from here to here was our overall reaction, which means that if you want to go from here to here, you can either go direct here or you can take this whole route until you reach the same products. So there is two ways. The first path is from here to here. Another path is to go all the way from here until here down, which means that this means that the enthalpy change of formation is equal to, so enthalpy change of formation is this part. So it's just going direct from here to here, which is the same as adding all these up. So 1 plus 2 plus 3 plus 4 plus 5. So it's the same as going through the whole route over here, which means that what we will do is we will add delta H atomization of sodium plus delta H ionization energy of sodium plus delta H atomization of chlorine plus delta H electron affinity, the first electron affinity of chlorine plus delta H lattice energy. And that will be your overall equation. And we will use this in past papers that we will be solving. And this is a very important concept to understand. So make sure that you have understood this well, how we form the Born-Haber cycle, why are some of these going up and some of these going down, and how we form this equation over here. Right, so let's take another example of a Born-Haber cycle. And this time I'll be doing of magnesium chloride. Now, I'll just be explaining to you the concept of how this is done because we have already done one example of drawing it from scratch. So again, if you want to draw the Born-Haber cycle, it's best to first identify the equation for it. So magnesium chloride is made from magnesium and chlorine. So you will have Mg plus Cl2 gives you MgCl2, right? But remember the state. So magnesium is solid, chlorine is a gas, and magnesium chloride is a solid. This is our overall equation. And what's delta H is this? This is delta H of formation, right? Because you're forming 1 mole of an ionic compound from its elements under standard conditions. So this is delta HF. And we remember we need some sort of intermediate over here in between. Now, if this is an ionic compound, you can form this from its ions. So we can have Mg plus plus Cl minus gives you this one, right? But again, remember, if you want the ions to form this, this has to be in gaseous state. So this has to be a gas, and this has to be a gas. And we have to balance the equation as well. So if there is 2 chlorines here, we have to keep 2 chlorines over here as well. So this will be our intermediate, which will form the magnesium chloride as a solid. And this is delta H lattice, right? Because solid forms from gaseous ions. Then here, if we want to go from these two, we can just keep a arrow like this down over here. And just in our first example, we can just call this delta H. We saw that this delta H is a combination of a lot of stuff. So we just call it delta H, and yeah, then we can go on to draw the Born-Haber cycle for this. So again, we started with the magnesium plus Cl2. So you start with the reactants part over here, right? And then the magnesium has to be converted into magnesium 2 plus. So there's 2 steps to this. The first step is it has to be converted to a gas, which is atomization, and it has to remove its electrons. Now here is a tricky part because you are going from Mg to Mg2 plus. How many electrons have you removed? You've removed 2 electrons from here, right? Not one. So this will be what? This will be the first ionization energy of magnesium plus the second ionization energy, and not uh, first times 2. I've seen some people make this mistake, and this is wrong. Don't do the first ionization energy times 2. This is 2 electrons being removed, so this actually takes place in 2 steps. The first step is Mg becoming Mg plus, and then Mg plus becoming Mg2 plus. So you have to take the first ionization energy plus the second one, right? So this here is the first part over here where Mg becomes Mg plus. Then it's becoming Mg2 plus. And remember, all these are endothermic reactions, atomization and ionization energy. Now, when we're done with the Mg part, we go to the Cl2 part. Again, this one has to become an atom first, and then we have to add electrons to it to form this 2Cl minus. So the first step is we are converting the Cl2 into the chlorine atom, which is atomization. But the thing is, we have to balance this here. If you have Cl2 and you want to form a chlorine atom, Cl, you can you can keep half over here, half Cl2, and it's gonna work. And this is the normal atomization that we know over here. But the issue is in the reactants here we have one Cl2. Like this is fixed over here. We can't force it to be half. So that means that this will be the atomization but just times 2. So you have to take the Cl2 as how it is, but you have to keep 2Cl over here, right? So this will be atomization, but it's just that it's gonna be multiplied by 2. Now when you form the 2Cl, then again it has to gain 1 electron, right? So the chlorine has to become Cl minus. So this is the first electron affinity, but you have two of them. Okay, and so both the chlorines have become 2Cl minus 1. So this will be 2 times the first electron affinity. This time we don't do the first electron affinity plus the second one. We don't do that. Why is it? Because you just form a negative 1 here. You are just you are just you are getting the first electron affinity, but it's just that there is 2 chlorine atoms this time. If it was Cl2 minus, that will have been the first electron affinity plus the second one. But this is just 2 times the Cl negative 1 ion. And if you remember, we said that electron affinity is exothermic, so that's why this goes down. Then finally, when you form this intermediate, that's when we actually can go on to form the main solid over here. And you should try to make this go down until lower than this one, because the overall reaction is usually exothermic. So enthalpy change of formation is exothermic, and enthalpy change of lattice is also exothermic. So you'll go on to form MgCl2, which will be your final compound. Now, again, you can make a reaction out of this. So the reaction here will be delta HF. This is the straight. This is the overall reaction. You can either go here or you can take this long way until you reach here. So delta HF equals to basically just add this atomization plus I1 plus I2 plus 2 times this plus this plus this. So I'll just label all that from here until here as delta H. So it's going to be delta H plus the delta H of lattice. And that's how you solve questions relating to Born-Haber cycle. Now also one thing that I want you to be aware about, which will help us in solving questions, is the relation between between the bond energy and delta H atomization. Okay, so these two are very important concepts. Let's take an example of chlorine, right? Cl2 molecule. Cl2 molecule is drawn like this. Now, what does bond energy mean? It's the energy required to break this Cl-Cl bond, right? So you're going from Cl2 and you're forming 2Cl. It's gas. This is the bond energy. And If we talk about atomization, what is the equation for the atomization of chlorine? This was Cl2 gas becoming Cl gas. And here we keep F over here. Now, do you see a relation between these two equations? This one, the first one, is like times 2 of this one, right? It's basically the same thing but just multiplied by 2. So you can see that Mott energy is equal to 2 times delta H atomization. And this is a very important equation, and we will be using this a lot in solving our past paper questions. So just keep this in mind.